In problem 9, we're going to perform a one proportion lower tail test. And the reason why this is a lower tail test is because in this statement, you want to know if the senator will lose her upcoming election. When a person loses an election, that means the proportion of the vote that they get is less than 0.5. So the alternative hypothesis is the true proportion, P, is less than 0.5, which means the true proportion is greater than or equal to 0.5 in the null hypothesis. Now, because this is a lower tail test, the critical value is negative, and we can find it in the t-table in the infinity row in column 0.01. So in column 0.01 and row infinity, we can find a z critical value, which is 2.326. The values in the infinity row are z values, standard normal values. I'm going to copy this value and then paste it into Cengage Now. After pasting it into Cengage Now, we have to make it negative because the alternative hypothesis indicates that this is a lower tail test. I have copied part C of the question from Cengage Now into Excel and will compute the test statistic to 4 decimals. To do that, I first must calculate the point estimate of the population proportion, P bar, the variance of the underlying variable, the difference between the point estimate of the proportion and the hypothesized value, which is 0.5, the variance of the sample proportion, the standard error of the proportion. Now, the point estimate of the proportion is 0.43. It is given in the problem. The sample size is 125. Because this is a one proportion hypothesis test and the hypothesized value is 0.5, the variance of the underlying variable is the hypothesized value, 0.5, times 1 minus 0.5. The difference between the point estimate of the proportion and the hypothesized value is equal to P bar minus the hypothesized value of 0.5. The variance of the sample proportion is going to be smaller than the sigma squared that we calculated above because it is equal to the sigma squared we calculated divided by the sample size. The standard deviation of the sample proportion is equal to the standard error of the proportion. So we just take the square root of the sample proportion. The test statistic is equal to the point estimate of the difference between the proportion of voters voting for the senator and the hypothesized value, 0.5. We divide that difference by the standard error. The test statistic to 4 decimals is negative 1.5652. I've copied the test statistic into Cengage Now, and now I need to conclude in part C. To conclude in part C, we have to compare the test statistic to the critical value. If the test statistic is less than the critical value, then we have evidence in support of the alternative. Otherwise, we have evidence in support of the null. Because the test statistic is greater than the critical value, we are not able to reject the null. Thus, we cannot conclude that Senator Smith's support is less than 50%. This suggests that the senator will not lose the election. The problem in part D is identical to that of C, except now we have a sample of over 1,500 voters. So we're going to redo what we did in part C, but with a sample size that is much, much larger. I've already copied all the numbers and part D's problem statement into Excel. So again, the sample proportion is 0.43. The sample size is now 1770. The sigma squared is no different than it was before. It is equal to the hypothesized proportion, 0.5, times 1 minus the hypothesized proportion, 0.5. The difference is no different than it was before. It is equal to the sample proportion minus the hypothesized proportion, 0.5. The variance of the sample proportion is much smaller than it was in part C because we're dividing the same sigma squared by a larger sample size. The standard error is the square root of the variance of the sample proportion. The test statistic is the point estimate of the difference and the standard error. For decimals, the test statistic is negative 5.8900. We're going to copy that into Cengage now. Now this time, the test statistic is less than the critical value, which means we can reject the null hypothesis. Thus, we can conclude that Senator Smith's support is less than 50%, which suggests that Senator Smith will lose the election. The larger sample size reduces the standard error. When the sample size was 1770, the standard error was 0.01188. When the sample size is 125, the standard error was about 4 times bigger than that, 0.04472. In part F, we have to determine which of these statements are true. And 2 of the statements involve type 1 error. 2 of the statements involve type 2 error. To reduce the likelihood of making a type 1 error, you lower the value of significance. To reduce the probability of making a type 2 error, you can increase the sample size. So the answer here to part F is increase in sample size lowers the probability of making a type 2 error. Now I'm going to check my work and we should get all the answers correct. And we do.